So today we want to continue discussing how we verify implementations of distributed systems in Verity. Remember, we're doing this because there really are critical systems. A lot of the things we do every day rely on distributed systems. And when those go down, people suffer. And it's hard to get right because there's a lot of different kinds of failures that systems have to tolerate. And it's really difficult to keep track of all the possible orderings and sequences of failures and recoveries that can happen. So we want to be able to prove this stuff. Now, last time we ended the slide part on this slide, where basically we set out this plan. We want to sort of formalize network semantics. And we started seeing how to do that in the simple DS model, the mini Verity, if you will, right? So we had the step relations that described which worlds a world could step to, right? And those relations captured different kinds of faults. But the key thing that Verity really enables is transforming systems and carrying their proofs across semantics, right? So I want to take a system which is correct, assuming certain kinds of faults don't happen, and automatically transform it into a system that can handle more faults. So that's what we're going to get into today, and we're going to still be talking a little bit in the simple DS model. But the other big thing I wanted to do is actually start to kind of walk through some code from actual Verity, so that when you guys are looking at that later today, maybe it'll be less bewildering. Okay, so we have these kinds of failures that can happen. Distributed systems are concurrent. They have timeouts, message delivery, node failure, node crashes, and concurrent state changes. So to handle this, we already talked about defining distributed systems and how to give them semantics, and we showed a small example proving safety. But I wanted to go back over those things kind of in slideware at a high level, hopefully to make sure that the intuition is concretizing in your mind. And then I want to show a cartoon version of reusable verified fault tolerance, and then we'll actually look at some examples in Coq. Okay, so we saw how to define systems, right? Basically, we define some base types for input, output, what nodes are in the system, what messages those nodes can exchange to the network, and then also providing event handlers, right? So like, handle message, handle input. Those describe how the system reacts when something from the external world or from another node interacts with it. And once we have those, then we encoded network semantics to describe their behavior, right? And so the network semantics basically had some triple where we had the set of packets in the network, the local state at every node, as well as a trace of all the external interactions that our system has had with clients. And this is typically the thing we want to write our specifications over. And we described how that can step to another world, right? And those rules, here's this message delivery rule, but written in Greek instead. And sometimes I find it's useful to go back and forth between these. I've definitely been trying to read a POPL paper and written the Greek rules in Coq because I couldn't understand what the Greek rules were. You go the other way a lot when you're writing papers. So this is the same thing we had for our message delivery yesterday, right? All it's really saying is, if there's some message from source to dest with payload M in the network, and I run the event handler for dest in its current state on that message to get some new state, some outputs, and some more packets to send, then I update the new world. The world I step to is just like the old one, except I've included the packets that the destination wanted to send, right? The P prime comes down and goes in the network. I update the state, so P prime state now reflects this updated state. And I send the outputs, or I added the trace, I sent those outputs to the external client. And we have a bunch of these rules. And what's nice is that we can kind of mix and match them to capture different kinds of failure, right? So one of the things that you're encouraged to think about for the homework was duplication. So here we have a notion of duplication, right? Where if there's something in the network, we can take a step where we just add it. There's another way to encode duplication, which we'll see in Coq here in a few minutes. You also have drops, right? So you have some message in the network. You can step to another network that just doesn't have that message, right? And we also have things like timeouts. And we haven't talked about timeouts yet, but we'll see a little bit of that today when we're going through Verity code. So for some kinds of faults, you need some other mechanism to handle it, right? If the network can drop packets, right, I need some way of detecting that and telling a sender that I missed something, right? If I haven't heard from you in a while, I don't know if it's that you didn't reply or the network was just dropping packets. So you need some kind of timeout mechanism as well. And so we're going to see systems that have timeout handlers, which can sort of fire at any time. But what's nice is that this is a really flexible way for encoding fault models, encoding the assumptions about how distributed systems behave, how their states evolve over time. And notice, right, these are sort of always parameterized by the handlers, by the actual implementation of the system. OK. And so we have this sort of menagerie, right, this zoo of network semantics with increasingly adversarial fault models. And what's tricky is that what we really want is we would ideally want to always have guarantees. We always want to prove invariance about our system in the most adversarial semantics, right? That sort of gives us the most confidence that our intuitions about how that system behaves will actually hold in practice. When I actually go and run it on a real network made of copper, right, what that system does will correspond to what I proved it would do. But it's hard to do those proofs. And it's hard for a couple reasons. So one reason is something we've already seen, right? When you go to prove a system, there's this fundamental difficulty that you write down your spec, and you want to prove it. What are you going to do? Well, you need to say, it better be true in the initial state, right? Because that's definitely a reachable world, right? And then what you want to show is you need to show it's true in any possible state you could ever reach. There's only one way we're going to be able to do that, which is induction. And so what we're going to do is we're going to say, well, suppose that I'm in one of the states that I've said is safe. Now what I'll need to show in this inductive case is that if I take a step, right, to another reachable world, that I'm still safe. And the problem is that most of the times that spec is too weak, right? There are states that aren't reachable that satisfy the spec. And it's not the case that starting from those states will get you back to an OK state, right? So typically, this is where a lot of wailing and gnashing of teeth occurs during verification of systems, distributed systems included. So we have to play this game of strengthening our induction hypothesis to find what one of my students calls the little bear hypothesis. I don't know if people know the fairy tale of the three little bears, or the three bears, Goldilocks and the three bears, that's the one, right? So like the one parent's bear porridge is always too hot, the other parent bear's porridge is always too cold, but the baby bear's porridge is always just right. And that's the game we have to play when we try to find specifications that, invariants that are inductive, right? If they're too strong, they will be able to imply themselves, right? For example, if I just use false, I can definitely imply myself, right? If I'm in a state that satisfies false, I take a step, false will still be true. If they're too weak, right, if it's just true, I don't know anything, particular about the state or the network, I'll definitely be able to establish it initially, but I won't be able to prove the invariant again after a step. So this is this balancing game that we play to find these little bear invariants. But there's a second problem, right? So we've already seen this problem. There's a second problem when we start to verify these distributed systems, which is that for a given target semantics, for a given kind of network, a given environment we want to execute in, the way we handle faults in that semantics is going to be the same across systems over and over. And if we don't do something about it, we're going to end up doing the same kind of proof, the same kind of reasoning for all those systems. So instead, what we're going to try to do in Verity is come up with a way that we can verify a system transformer. Right? So we're going to take as input, we're going to have a functor, or we'll use type classes or whatever. We're going to basically have a way of taking as input a system and producing another system. So here, you can imagine something like TCP, right? So you take a system that assumes it has reliable message delivery. You're going to transform it into a system that works even when message, works on a network where message delivery is not reliable, right? It's going to change the way it sends messages. It's going to add timeouts. It's going to have ways of handling messages not being delivered successfully. And then we're going to prove a theorem, right? And this is a higher order specification. I'm going to say, okay, well, for any state of the system, any world, and any property, if that property was true for the original system, it's also going to be true in this more adversarial semantics after I apply the transformer. Now this is almost, if you've ever hacked on CompCert or verified a compiler, this is almost like what we try to prove when we verify compilers, right? Normally those things look something like, for any behavior my source program has, my target program, my output program, my assembly, has the exact same behavior. Now notice here we're not quite saying that, right? This isn't quite like traditional compiler verification. We've made a small tweak. And the reason is that we're not always going to be able to actually guarantee equivalence, right? For example, if I'm in the in-order semantics, the ideal semantics, where messages are always delivered in the order they were sent, there are things I can prove about my behavior in that semantics that are just not provable in more adversarial models, right? In particular, things like liveness. In the ideal semantics, messages are always delivered, and they're delivered in order, right? So it's fair, I know that the system is live, right? Like I can always stab, like if I send a message, it'll get delivered. In the more adversarial semantics, where you have drops, I don't have that guarantee. The network could just drop packets forever, and nothing would ever happen. So we're going to have this wiggle room, right? We're going to have to lift the property from the friendly semantics into an analog of the property in the network semantics. So we'll see a little bit of that. Yes?
Is the need to weaken the kind of guarantees you get similar to like the CAP theorem or the consequences of the CAP theorem?
Yeah, that's right. So for people who aren't familiar, so the question was, what does this have to do with the CAP theorem, right? I know from distributed systems that in some kinds of fault models, certain things are impossible, and in other friendlier fault models are not. Is that the kind of thing going on here and why we have to do the analog? Yeah, that's a great intuition, and it is that kind of stuff. So the CAP theorem basically says, look, if you're assuming that messages can be dropped, right, and nodes can crash, message can be reordered, all of this, there's actually no way for nodes to simultaneously all know, agree on some state, and for the system to be alive. Right? So you're going to have to choose. You can have consistency, you can have availability, or you can have partition tolerance. And you can't have all three, right? So CAP sort of, I think, is choose two. So there are these kinds of impossibility results, things that just you can't build a distributed system to do if the fault model is adversarial enough. Okay, and so anyway, so the idea here is that what we're going to get by doing this is we're going to be able to separate concerns, right? We're going to be able to tease apart a transformer where we just reason about fault tolerance, we do proofs about how fault tolerance works, separately from our application logic. And that means that somebody building a system only needs to think about what their system should do when things are going well, right? And then they can apply this transformer and get a system that does the right thing even when faults are happening.
So is this weakening of the proposition making explicit the notion of leaky abstractions?
So the question is, does this make explicit leaky abstractions? I don't. Can you expand on leaky abstraction more?
So the idea of TCP is being able to build reliable message passing over a faulty network, but obviously
it's not quite true.
Yeah.
Yeah, that's a good way to put it, right? TCP doesn't actually give you the ideal semantics, right? It gives you something close, but it's not quite right. Yeah. And another thing that people might be worried about here is that, hey, you're telling me that you're going to give me the analog of my property, but that's not my spec. That makes me nervous, right? So the idea is that really this is the property for the system. You should still have a final theorem about the result of TCPS. Right? And you're going to use this lifted version for proving that final end-to-end result. So that's sort of, at the end of the day, you want to prove your final thing. So even if there are leaky abstractions, and this lift might do something kind of dicey to make us nervous, we should have an end-to-end correctness theorem that, this gets used as a lemma n, so that we know we're safe. Any other questions?
So I guess is it hopefully the case that if P was weak enough to start with, then lift TCP on TCPS implies P evac?
So for most systems, that won't quite be true. I thought about actually doing an exercise like this, like, hey, come up with a semantics in a system where that is true. I mean, if you're in the exact same semantics, that'll often be true, right? And sometimes you do that. And tomorrow, we'll actually talk more about why you might want a system transformer when you're not even adding new faults. So in those cases, typically you can get both directions. But a lot of times you are going to have to give something up. Yeah. Okay, so in Verity, and we're going to see some of these today, in Verity we built a bunch of different kinds of system transformers. The big one is the Raft state machine replication protocol, which allows you to take a state machine and run on a bunch of different nodes and know that as long as half of them haven't crashed, things are still going to be going well. We'll see the primary backup system today, so it's going to take some application and duplicate it. It's going to be a lot like that counter system we saw. We have something kind of like TCP with sequence numbering, which we'll talk about. And then tomorrow we'll talk more about, it turns out that we can actually use this same mechanism of a verified system transformer to capture things that are helpful for proofs, things like ghost variables, right? This is a mechanism you want when you're trying to verify the system. We can actually just encode that as a VST. So it turns out that the Verity framework can not just use, I'm sorry, I shouldn't say VST, because that's Andrew's thing. Verified system transformer. Use a verified system transformer not just for building better distributed systems, but also in a way for extending our own framework, right? To make the framework itself more powerful, more general, more usable. Okay, so we're going to switch now back to Code, but wanted to again mention all the wonderful people I work with and how lucky I am to work with them. Anything I say that's good is to their credit. Anything I say that's bad is me messing up their words. But yeah. Okay, so the first thing I wanted to do really quickly, just to make sure that we got to it. Yeah, also I learned about horizontal, or vertical rather, split. Hopefully this will work better. Okay, one thing I wanted to do real quick before we jump into Verity. So right now we're in the simple DS sort of directory for lecture 2, but this is the same thing basically we saw last time. There are a couple tweaks. I figured out why I thought you couldn't have definitions in module types, by the way. It turns out that literacy is important. So when I was porting from the type classes over to the module version, I read this sentence and just interpreted it way too strictly. So in my defense, it wasn't just like completely made up, but it is important to be literate, otherwise you get called out by bigwigs during your lecture. Okay, so anyway, so here we're in the network semantics from simple DS. And just to remind people, right, this was the ideal semantics we saw last time. You get an input, you're on the handler, you step from the world you were in when you got the input to one where you've updated your state, you may have put some messages on the network, and you recorded the fact that you had that interaction with the client in the trace. And then we also saw the shuffle step semantics. I was thinking about trying to do a shuffle dance step. Do you guys know the shuffle? But I think I would probably just fall over. So this one, right, is almost the same. It's slightly more adversarial in that when we go to deliver a message, instead of delivering the oldest message, right, instead we just pick any message we want in the network. Right? The semantics can deliver any message, so you don't have any guarantee on order. So how would you build, just at a high level conceptually, what would you do if you wanted to take a system that worked in the ideal semantics and translate it to work in the shuffle semantics?
Add sequence numbers?
Yeah, so the answer is add sequence numbers. Can you tell everybody what sequence numbers are?
So just every message that each node sends, it adds like an incrementing number to the packet in the transform system.
And okay, so now what I'm going to do is I'm going to take a system designed to work in the ideal semantics, right? And I'm going to wrap it. And every time that it gets a message, now it's that message is going to be tagged with a counter. I'll strip that off. I'll hand it to the underlying system, right? The thing I'm wrapping, it'll respond with something else. But I'll interpose on all of its messages and tag those with fresh numbers and send them out, right? Right. So this way you can tell if you get a message that's out of order, you can tell that something happened. But how can you tell?
I have another question.
So there's one other part here, right? So it's not just that you tag those numbers. Every node also needs to track for all other nodes the biggest number it's seen so far from that node. And if it gets a message that's past that, right, it needs to sort of either ignore it and just hope that somebody will retransmit, or buffer it, right, until it gets the actual true next message. And we'll see, actually we're going to see that